So we have a few minutes until your colleagues join. If you have any questions, whether in the project, in quiz 4, or I think you already saw the grades and the answers. The answer should be there. If you have any question, anything, we have a couple of minutes. Okay. Today, inshallah, we are concluding our course. We are finishing on chapter 9, the design of jet propeller aircraft. And as you've probably seen last time, there isn't really much difference in the procedure as well as the calculations in jet propelled aircraft from the propeller aircraft. Slightly different performance equations, slightly different handling of the thrust to weight ratio, the air power to weight ratio, and so on, but not really much of change. So again, think of the example we are going through, or the chapter we are going through, and a solved example. Remind you what we did last time. We were talking about the design of the Boeing 727, which was required to be a short to medium range transport aircraft, operational from smaller airports that were not accessible to larger initial larger jets. We're talking the 707, 747s. So there was a set of requirements, and last time from the range requirement, we estimated the empty weights of the aircraft. No? Okay, I need to mute. Okay, so we estimated the empty weight of the aircraft, and the procedure to estimation of the empty weight was the same, with the exception of the specific fuel consumption. That was different for jet aircraft. And we reached a value of the empty weight. Then we used the calculation of equation of the total weight, and turned out to be 100,000. But that's not the only way to estimate the weight. That's a very rough way, but it was suitable for us here in AE240. When you get to 427, inshallah, you realize that we can estimate the empty weight not only by looking to a graph, just like we did in the project, but using information of different categories of aircraft, transport aircraft, jet aircraft, and so on. Each one of them would have like a separate curve where we can estimate the empty weight of the aircraft from. Okay, and sometimes it gives, not sometimes, I think always it gives a better estimate than the way we did it here in AE240. So that's another way to look at things there. But in any case, we have estimated the total weight. The next key point in the design process was the estimation of the critical performance parameters. So all these were still in the weight estimation. I told you I will be scrolling the slides because they are solved examples, nothing new in here. Okay. So the estimation of the critical performance parameters, basically the CL max, the wing loading, and the thrust to weight ratio. So I want to spend more time discussing why certain choices were made, why certain decisions were made, because this is the critical thing in the design process, not the numerics. You can program the numerics and they will come up right. You have to be careful in selecting the values, but answering the question, why have 2 engine, not 3, or 3, not 2, to put them here? How come they did this? Is that the thing that you need to develop over the course of study in our department? So let's start with the maximum lift, CL. They had a difficulty in the CL. The reason was the aircraft was supposed to take off and land from short runways, relatively short runways. So they found they need a really high CL in order to do that, something around 2.6, 2.7, which is considerably high. At that time, the best flap was the double slotted flap, which would give up to 2.2. So they thought, let's have a triple slotted flap. And that's why the Boeing 727 was the first aircraft to have a triple slotted flap. You see 1, 2, 3. So we have a considerably large flap. That's a huge flap when it extends. You see the flap when extending, it's almost reaching the limits of the clearance with the ground. You are almost doubling the wing area in the part of the flap, of course, not outside, but in the part of your flap. So that would hugely increase the CL max. The CL max would reach a value of 2.6, 2.7 of the airfoil, of course, and it will come down for the actual 3D wing. But there is no free lunch in design. You get good thing, you also get bad thing. And the bad thing about flaps is, anyone knows here? What's the bad things about flaps? They increase CL max, but what else do they do?
Increase the drag.
Well, increase the drag is true, but it's a good thing. Remember, we extend the flaps to land. So increasing drag is not a bad thing. Okay. So there is another thing that comes with the increasing camber of the airfoil with the flap extension, which is the reduction in the stall angle. That's bad. That's very dangerous. The wing will no longer stall at 20 degrees, for example. If the flaps are retracted, it might stall at 8 degrees. Now that's very dangerous because the aircraft cannot slow enough, and if it's slowed enough, the wing will stall. So in order to solve this problem, engineers, not of the Boeing 727, but aerospace engineers in general, thought if we have a flap and we have a disadvantage of the flap, let's fix that disadvantage by having the leading edge devices, slats. So slats increase the CL max even more, but they also increase the stall angle. So for the 727, they developed, or they used the Kruger flap. Okay, Kruger flap is a little bit of like an extension, or it's folded in the wing and it would extend when the aircraft is landing. Let me show you what effect does that have on the of the aircraft. Now, if you look at here, this solid line down here is the CL alpha curve when there are no flaps extended. So flaps are up, slats are up. It's the clean configuration for which the aircraft flies. So that's the curve. It's good. It has a high stall angle of about 20 or 19 degrees, but the CL is not really that high. It's 1.2. Now that's not good. That's good in cruise, for example, but that's bad. I mean, the curve is good in cruise, but it's bad when it comes to takeoff and landing. You want to shorten the runway distance, you need to increase the CL max, so they use the flap, okay? If you do wind tunnel tests or do some analysis with the flaps, as you will learn in your aerodynamic courses, or we will have rough methods in 427, you will realize that the CL alpha curve will not be that solid line, it will be that dotted line. The CL max increased to about 2, which is good. But you see the problem? The wing would stall here before flap extension at 20. Now it would stall at about 9 degrees. Very dangerous, very unacceptable, because the angle of attack will be higher than 9 degrees during landing. Now with these leading edge devices or the slats, the ones in the front in here, these ones in here, or the ones that you see in here, these are the slats that we have. The CL will go even higher, so that's the CL max. But the best thing, or the most important thing, is that the stall angle is no longer 9, but it becomes maybe 18. So slats are used to fix the stall angle. So now with flaps and slats together, the CL increased to the required 2.8, and the stall angle is still high enough to be safe during landing. Okay. So back to the calculations. Wind tunnel test showed that the airfoil will have a CL max of about 2.9, and we know that this is with the triple slotted flap and the Kruger flap. Okay, not many aircraft has that triple slotted flap. Even modern aircraft like the 767 has only a double slotted flap. So if the airfoil has a CL max of 2.9, the wing will have a 0.9 of that. That's about 2.6, which is deemed acceptable. So that was the first parameters they calculated in the conceptual design, the CL max. Then comes the wing loading. In your design project, you calculated the wing loading based on the stall velocity as well as the landing. And it's exactly the same thing here. Only the numbers are different. So based on the stall, wing loading is 86. Based on the landing distance, the wing loading, exactly everything in the landing is the same. The wing loading would be 178. Of course, you now know that you will pick the lowest value of this. So the lowest of the two values is the 86. And if I divide W0 over the 86, that will give me 1,845 square feet for wing area. So that was the first important parameter, the wing loading. The second important parameter, the wing loading. The third is the thrust-weight ratio. In your design project, you calculated the thrust-weight ratio based on the takeoff distance, the rate of climb, and the maximum velocity. And it's basically the same here. No change whatsoever in the equations. So in the takeoff distance, let's see, SG, still SG, T over W is a, let me just scroll to the number. So it turns out to be 0.08. So takeoff distance can be satisfied with a thrust-weight ratio of 0.08. 8% of the weight of the aircraft is the thrust. Okay, and that was well within the range of other aircraft. Now, for the maximum speed, you will need the S-sweat of the aircraft, but we don't have a configuration yet. So there are other ways to estimate the S-sweat over S of the aircraft. And doing so, we reach a thrust-weight ratio of 0.6. Now that's huge. That's a huge thrust-weight ratio. 60% of the weight. Now, so we might have a problem here satisfying that, finding engines that will give that value. Okay, the third thrust-weight ratio came from the rate of climb, and a decent 0.15 T over W was obtained from the equation of the rate of climb. So now you have three values for thrust-weight ratio, 0.08, 0.6, 0.156, and by now you know you will have to pick the highest one. So it's the 0.6. Okay, so these are the other parameters that came along during the analysis, similar exactly to what we had, CD0, K. Nothing changes in here because these do not depend on the type of propulsion. They depend only on the aerodynamics of the aircraft. Okay, so now we are ready for step number 4. I'll stop for a minute and see if you have questions before we get to step number 4, the configuration layout, because that's where I want to spend most of the time. Okay. Now, in configuration, you have to choose several things. The fuselage, the wing, CG, the landing gear, and so on. So they thought, how will the aircraft look like? So it was deemed to have, is it high wing or low wing or mid wing? So since it's going to be a passenger aircraft that has cargo under belly and it will have passengers on the top, they said we can have a middle wing. Okay, because the wing will be continuous and I'll still have room above the wing for the passengers and below the wing for the cargo. So it is a middle wing configuration. And then came the issue of the engines. And the engine issue was tricky. Remember, you need a lot of thrust. So you can achieve this by either 2 large engines or 3 smaller engines or even 4 smaller engines. So you will see in the next 5 minutes different aspects are going to be mixed together in order to come up with the decisions. Let's look at how things go. First, let's consider the two engines choice. If I want to have two engines, the problem with two engines is that with a large thrust, the engines have to be real big. And if you have a mid to low wing, that you might have a problem here with the clearance under the wing. Designers face this whenever they need a big engine and they think to mount it under the wing. The same type of problem emerged in the latest Boeing 737 MAX. Remember the problem was at 737 MAX? The original problem started because they didn't have enough room for the larger engine, new engine under the wing. So two engines under the wing was not a good choice. They excluded that. They will not be able to do that. Okay, so two engines attached to the fuselage will be also too much because the engines have to be huge, putting a lot of stress on the fuselage. So the other choice would be to go 3 or 4 engines. 4 engines are good in a sense that we can have 4 smaller engines underneath the wing. I can have 2 here and I can have 2 here, just like the 707 and the 777, all of these. So I can have 2 smaller engines. Remember back then in the 1960s, they didn't have very high bypass ratio turbofans. We are talking about a turbofan of a bypass ratio of 3 to 4. Today we are talking about bypass ratio 6 to 8, sometimes 10. So the engines were not really that big. So they can fit 2 engines here and 2 engines here to get the thrust. But a problem with 4 engines is that you have parts. And in engineering in general, the more moving parts you have, the more chances of something going wrong. In technical terms, that means 4 engines will have less reliability than 3 engines, and these will have less than 2 engines. It's just like Murphy's Law, something will go wrong. So if you have fewer moving parts, you have better reliability. So by the experience of Boeing, having designed several aircraft before, they know that the direct operational cost, which are the maintenance, would increase with the increased numbers of engines. But the increase is not linear and it's not exponential. It starts like a linear and then becomes like that. Now they know that, they have this data, they manufacture aircraft. So if 2 engines are excluded because they will be too big, they said, okay, we can either go 3 or 4, but 4 will mean more maintenance cost because of the chance of something might go wrong. Okay, so let's go 3. So their choice was 3 engines. Now 3 engines, you have the problem, where are you going to put the 3rd engine? So one choice was that the 3rd engine would be completely above the fuselage, just like the MD-11, where you have the intake in here and the exhaust in here. But they thought they have enough room in the tail cone to put the engine under the wing, under the vertical tail. So the engine here is under the vertical tail and you can see the nozzle of the engine. Whereas the intake of the engine was put above the fuselage and flow would be directing through the ducts into the jet engine. So that's the intake in here, separated from the engine and the nozzle. Wind tunnel test showed that this would be better in terms of drag than the all exposed engine. So they came up with this configuration for the 3rd engine, and now they thought to put the 2 other engines also in the fuselage rather than underneath the wing, because they want the wing to be as low as possible. So you see, things are mixed together. We haven't seen a single equation, but you have to think from different perspectives, from a structural perspective, operation, maintenance, costs, reliability, thrust, and so on. This is the kind of brainstorming a team would need at the very beginning in order to come up with the concept. Okay, so that's how was the design developed. So 3 engines in the back, 2 engines underneath the wing was excluded, and they came up with this configuration. That's the final engine arrangement of the aircraft. You don't exclude this from the very beginning. They continued with both for us to some point to see if maybe this one would have a major advantage than that one, up to the point where a decision was made, let's go with this configuration. Okay. Now, with the engine choice, the engine choice dictated other changes in the design. For example, if you have the engines back in here, you must use the T-tail up there so that you have room. You don't want the tail to be directly behind the exhaust of the engine. So they had a T-tail. If you have a T-tail, the vertical tail must be stronger to carry the load of the horizontal tail. So that's why you see the vertical tail here, relatively larger than what you expect in an aircraft. You see the taper ratio of the vertical tail, almost 1. It doesn't taper because I need all the core that I can have in order to carry the load of the horizontal tail. So that's how was the configuration developed. Any questions up to this point? Okay. Once the concept was developed, now we need to put some numbers. So how big the fuselage is going to be. So based on historical data, they try to estimate the length, then they try to calculate the diameter based on the seating arrangement, decided to have 3 and 3 single aisle aircraft. And based on the industry norm for, let me jump a little bit and I will go back. Based on the industry norm of the distances between the seats, this is the aisle width, the height and the height here, there are certain industry numbers that you cannot violate. You cannot make the height of an aircraft 1.5 meters. Height of the fuselage, that would be too short. People will be bending all the time, right? So there is like a minimum height that can be there. Minimum height about the head, or it will not be comfortable. Distance between the seats. And we know this, I think we used like 3 feet in our design. And you'll see where that comes from. For passenger aircraft, the seat pitch would be between 38 to 40 inches. For first class, 34 to 36. That's about 3 feet. 36 inches is 3 feet for economy class. So this is like further information than what you had in AE 240. I had this table from AE 427 where we have more information about the different dimensions. Okay. So they use this in order to determine what would be the diameter of the fuselage. They decided they don't need much volume for the cargo below the floor, so they really didn't need a full circular cross-section. A full circular cross-section would be easy to calculate. That's why we did in AE240. But it will mean more friction, more unused volume underneath. And they wanted to have the smallest section possible. So they had a certain fuselage with a certain radius on the upper part and a different smaller radius on the lower part. And this will bring the fuselage height to be smaller than their baseline design of the 707. Okay. So it was considerably shorter in that dimension. Okay. So they sized the fuselage. Now comes for the wing configuration, and that's where it's exactly like we did in the project. So if you have the wing area from the wing loading and the total weight, I will proceed and calculate the aspect ratio, wing sweep, taper ratio, mean aerodynamic chord. Typically, these are exactly the same equations you had. Okay, so they came up with the wing. They decided to be a mid-wing for a structural consideration. The wing will be in the middle, so that it's continuous, passengers above, cargo below. And they calculated the volume of the fuel tank where they want to store fuel tank. So the fuel tank will be here, here, and here. Okay, and you see this? They designed the wing to be so strong that they can put fuel in the outside areas. In regular aircraft, we would not go beyond maybe the 1/3 or 1/2 of the wing. But they allowed storage of the wing in here. So the wing is very strong because they needed that for the medium range. So that was for the configuration, and based on the configuration, they started sizing the aircraft. Finding the CG of the aircraft. Again, the same equations that you used. Crew, passengers, payload, and the wing, they found the CG. For the tail, they used the tail configuration because of the engines in the back. They sized the tail. That means they found what is SVT and SHT. And the tail ratios, the ones that we used in the textbook in chapter 8, the ones that you do remember what were the values of your CVT and CHT for your aircraft? Anyone? The tail volume coefficient, either horizontal or vertical. Was it 0.7? No. Okay. If most probably it was the 0.7 or 0.8 C horizontal tail, and C vertical tail was about 0.07. Now, these values that we had in the example in chapter 8 came from this table. So you see these values are only for general aviation, whether it's single engine or twin engine. But they would change considerably depending on the type of aircraft. So for this Boeing 727, which is a jet transport, C horizontal tail is 1 and C vertical tail is 0.09. Remember, this aircraft is heavier. It should handle in a different way than an aerobatic aircraft. So in your aerobatic aircraft, I don't expect you to use 1, of course. That would mean that the aircraft is so slow to respond. You are using smaller one. If you have used the Boeing 7 or the 4, it would still handle differently. I told you reduce that 0.7 a little bit, maybe 0.6 or 0.5. So for a jet trainer, for example, we are talking close 0.7, but for a jet fighter, it's 0.4. Okay, so the slower this value, the less is the control authority of the tail on the actions of the on the motion of the aircraft. So they size the tail from equations identical to what you have used. What is the volume tail coefficients? And then came the last part, the landing gear. Where are you gonna place the landing gear? With the aircraft having no engines underneath the wing, they were able to retract the landing gear directly into the fuselage. That means the landing gear can be short. It doesn't have to be a long landing gear. So they went for the tricycle landing gear, and the landing gear would retract into the fuselage. They calculated the static margin, turns out to be 0.1, good for an aircraft, and from there they placed the wing and they calculated the location of the wing relative to that of the fuselage, exactly as in chapter 8. Okay. They put the nose wheel at about 10 feet from the nose, and that was a question that I received yesterday. Why did we place the nose wheel in the example 2.5 feet from the nose? Well, there is no rule for this. You put the landing gear in a proper place so that the reaction on it, the F, is not that much, and you have room to retract it in the fuselage. In here, the landing gear will retract backwards. In the example that we had in the textbook, the landing gear would retract forward, and it was deemed enough. 2.5 feet, about 80 centimeters are more than enough, and we have room there, so let's put it. But in a transport aircraft, things are different. Let me show you the, if this is, no, I need one on the landing gear. Let me get in here. Now, it's somehow difficult for the landing gear to retract forward. You can, but it's difficult. Why? Because you have so many things here that occupies the volume. We have the radar at the nose. We have the avionics bay of the cockpit. Typically, it's underneath the cockpit. The avionics bay, electrical systems, and so on. So this area is kind of crowded. You have anti-icing system. So typically we cannot, in general, in most cases, we do not retract the landing gear forward. We retract the landing gear aft. Okay. So that's what dictates this area. Why was this area about 10 feet? Because we have so many things here to put. I cannot retract the landing gear in this area. And the main landing gear would retract in the fuselage, but the wing was not thick enough, so they had to devise this like pod, a little bit extra volume between the fuselage and the wing to house the landing gear when it retracts. So that was how the landing gear was designed, and they calculated the diameter of the landing gear exactly the same way you did in your quiz. So came up the main landing gear 48 inches. So that's about 120 centimeters in diameter. And the nose wheel was smaller than this, 25 inches, about 75 centimeters. Now, it's not as big as you might expect because we have two nose wheels. We have two wheels attached to the strut. So if you're thinking this is a little bit too small, remember we have two of these. And here we have two wheels per strut. So I have two on the right and two on the left. So that's why it wasn't really that bad, because the load is divided by two, not by one. Any questions up to the landing gear? Okay. So the next step, after they did the configuration, they found the configuration, they try to estimate the weight, the better estimation of the weight of the aircraft. That means calculating the weight of the wing, the tail, vertical. Similar to what you did in the exam. Again, there is no difference here between jet and propeller aircraft. The difference here is because of a transport aircraft and the general aviation aircraft. So this number was, the 10 here was 2.5 in your design. Because this 2.5 is the typical value for a general aviation aircraft, whereas here it's 10 for transport aircraft. The wing is thicker, stronger, more fuel, so it will be heavier. So the values here are different. They are not exactly the same, not because it's jet, but because it's a different category, transport aircraft. Now, yesterday, most teams had problems in the better weight estimate, because when you do so, the weight will increase way above your initial weight values. Now, in here, you realize that the weight actually increased above when they did the weight estimation. The total weight at the end, I'll just jump to show you my point. The total weight actually increased above the 100,000 they had before. But that wasn't a problem because they were trying to find out what is the value of the total weight. In our case, it was a problem because if the weight increase, you will be in a different category from light sport aircraft. We shouldn't increase above 1320. Here, they didn't have that limit. So it wasn't a problem then. Back then in the 1960s, they didn't have the composite technology, so they could not reduce these numbers by 0.9 as I suggested to you yesterday. If the wing, tail, and fuselage, only these four numbers are made of composites, I can reduce each one of these by about 10%. Composites technology allows me to reduce the weight of them by about 10%. Okay. So I advised you, you can reduce this by about 10% in here. Now, maybe it worked and maybe it didn't work. Why? If it doesn't work, then we have to think why it doesn't work to bring it down to that value. Because the values that we use, whether the 2.5 for the general aviation or the 10 for the transport aircraft, or by the way, it's 9 for fighters, and you will get that table in AE427. So your example were in here, you were talking in this design, but here is the big picture. These numbers are not like science-based. We didn't derive these numbers. We just approximately from similar aircraft. So the 2.5 represents a kind of average of all general aviation aircraft. 10 is a kind of average of many transports, from the huge Boeing 747 to the small aircraft. It's still a transport aircraft. So sometimes the numbers don't work for your design if you are not around the average. If your aircraft is too big or too small, these numbers will not work fine. Okay. So there are other ways to estimate that empty weight. Also, you had problems in calculating the exposed wing platform. Now, the way we calculated the exposed fuselage wing, exposed areas. The exposed areas for the wing should not be a problem because it's basically you look at the area of the wing outside the aircraft. This is the exposed area of the wing. It's less than S of the wing. You take out this part inside. So we can estimate S exposed of the wing with reasonable accuracy. The same goes for the tail. All I have to do is to take out the part of the tail that's inside the fuselage. So these are okay. Okay. Also for the vertical tail, by the way, this is a part of the tail that's inside the fuselage. I should take this part out. So this reduces the areas here considerably. If you made a mistake and used S instead of S exposed, then your weight will be too much. Also, some of you used S-wet. What do you mean by S-wet? The external surface area of the wing. That means the area above the wing and below the wing, the upper surface and the lower surface. Now that's too much. If you use S-wet, that means you have used double the area of the wing. So it is S exposed. Okay. Now, the way we estimated S exposed for the fuselage cores is not really a very accurate way, but it was reasonable for an example in the textbook of AU240. And because the general aviation aircraft had a very long nose in there. But in this aircraft, for example, if I want to distribute, I will take a cone, I will take a cylinder, and I will take another cone. So it will be 2 cones and 1 cylinder. Now, we are doing this because I don't have better tools, but now, hopefully soon, when you learn ME210, you will be able to draw these aircrafts or your design on SolidWorks. And in this case, you don't have to do the slides. You don't have to guess and try to estimate its exposed. You can get it directly from the software. Okay. And these are not the only 2 ways. There are several ways in between. I can make a model on 3D printer and find the external surface area. I can make a small model and try to estimate the surface size. So getting the exposed surface should not be a big problem if we have a model. So with the better weight estimate, that weight turned out to be 120. And here are the final values that we found for the parameter CL max, L over D, CD naught K, exactly the same way. Came the final task, or one before the final, task number 6, the performance analysis. Will this aircraft give me the takeoff distance, the landing distance, and the rate of climb that I want? So the proceeding of the performance analysis exactly as in chapter 8. So calculate the VSTOL, turns out to be okay, lower than what's expected. Landing distance okay, and takeoff distance again okay. Okay. So you saw now the application of the 6 key points of the design. Only the 7th is not discussed in details in the textbook, neither in chapter 8 or chapter 9. Then 7th is the optimization of the design, finalizing how to improve things a little bit, tweak them based on wind tunnel tests, simulations, and so on. Okay, any questions? Okay. So with this, we are done with the material of this course, EE240. You have, I hope you enjoyed it. I hope it was beneficial. I have a few announcements for the coming period. Inshallah, on Wednesday, we are going to have your presentations. So please be timely on the presentation. We will start sharp at 10 because we barely have time for the teams. Okay, no more than 10 minutes. Please practice with your team. Prepare one presentation, one solid presentation. Don't make it like everyone will have 2 slides and they are just disorganized and it's messy. Like practice and have it like 10, no more than 10 minutes in the presentation. Okay, you need to tell the whole story in that presentation. It's not about showing all the details. So you don't write an equation just like the one you see on screen now and try did you get each number. That's not the place to do that. You had the report to do that. Okay. So that's for the presentation. The other thing for the final exam, inshallah, it's going to be on December 28th as announced by the registrar. Now that's about 3 weeks from now. That's a long time. So I was thinking of having a review session somewhere between the 24th, 23rd, and the 26th, maybe. I'm trying to be like after your last exam before the AE 240. So I will send you a table, a doodle on the internet so that you can fill your, let me see what is going to be better, whether your exam schedule or your free timings, so that we can pick a slot. It's difficult for 39 students or 38 students. So please give me as many slots as possible. I'll probably be sending you only to put only your exam schedule, and I will pick any slot outside the exam schedule. So in this exam schedule, put the slots that you cannot be there, and I will try to find something that's common to all of you. Okay. The last announcement regarding your grades. So when you submit tonight, inshallah, the bonus report, I will have everything with the exception of the final exam. So maybe by the middle of next week, they will be finalized and sent to you to check against your records. Just in case I made a mistake, anything, just get back to me within the next week. The only part that's not or that changed from what you had in the syllabus is the oral exam. We were waiting to have oral exams. In the syllabus at the very beginning of the semester, I put oral exam just in case we don't have finals. KFPM had oral exams last semester because we didn't have finals, but since you are going to have a final exam, there is no point anymore in an oral exam. So I'm going to distribute the grades of the oral exam amongst different activities, the final presentation, the discussion of the presentation, and other activities. So the weights will change slightly. Things that were like 5% maybe will be 6% and so on. I'll try to maximize the benefit, of course, for all of this, but the oral exam grade will not be added to the final written exam. The final written exam is still as is on this syllabus. Okay, I think that's all I had. So we have about 5 minutes. If you have any questions, anything. Because you still have about 12 hours until the deadline.
Yes, Doctor.
Yes.
Do we have to get the distance, takeoff distance from cement and grass, or just one?
Yeah, when I think one of your colleagues asked this before, I told you for grass, the difference would be the coefficient of friction. So instead of the mu equal 0.4, it will be the landing, and instead of mu would be 0.4, it's going to be about 0.35. Okay, that wouldn't affect your calculations considerably. So I wouldn't go there. No, I would say that's not the right time, given only that you have 12 hours to go and do that. Okay.
No, I mean, do I have to put two values or just one of them, the gross?
No, typically, of course, in real life, we'll put two values. In fact, we'll put more depending on the requirements. So if you have two values, if you already calculate them, put the two. Yes. But if you are still going to do them, I would rather you focus on finalizing the report than doing new calcs. It's not a good idea to start doing calcs right before the submission. Just finalize the report and submit it. Okay, any other questions? Okay, so I hope this course was help for you to realize what exactly you need to learn in the coming 2 years. You need to learn a lot of aerodynamics, to have better ways to calculate CL max, CL slope, because these are important in the design process. You need to learn a lot of propulsion, thrust weight ratio, considerations in the operation of aircrafts and the use of engines, a lot of controls, stability. So that by the time, inshallah, you get to AE 427, you are with this foundation and all these courses, you will be more than prepared, inshallah, to tackle more advanced issues in the design of aircraft. So I'll see you, inshallah, on Sunday. Don't forget.